And so the recording is on now. So welcome to everybody. And for this new workshop, again, Olivier Garde, who is the organizer of the meeting, is with us, but he cannot speak because he has a poor connection, internet connection. So I will manage this meeting tonight, or today for most of you. And so it will be about Python. And as you probably know, for me, Python is something very important. This is an important language for the astronomers for several reasons. When we are doing spectroscopy, I know that we have to put the hands on. We cannot, we need to open source software at some points because we have to do our own process tool. We have to get some tools to manage our data. And usually speaking, we cannot use only standard software, and it's important to be able to put the hands on. And the Python software language is very, very important for this. It's good for this because it is very, very used in the astronomy world. So the community is huge. The general Python community is huge, and the community using Python in astronomy and spectroscopy is also huge. So this is a language which is easy to learn. It is a very general language, so you can do some low-level scripts, and you can do high-level structured program. And so it's very wide, and this is, I know it takes always some time to learn a language, but really it is worthwhile to learn the Python, to spend some time to do it, because this is a very, very useful language for what we're doing. Okay, so that's it for this presentation. Again, don't hesitate to ask any question. And now I give the microphone to Matthieu and to Vincent. So I think this will be Matthieu who will speak first. And let's go and have a good workshop. Thank you very much for your job, Matthieu and Vincent. And by the way, last week we had very, very good comments, so I'm sure that it will be again wonderful. Okay.
I hope. Thank you, François. Hello, everybody. I'm happy to see you here tonight or this morning for some of you. I will share my screen first. Up. Don't move. Okay. I think it. Yeah. Hop. Ok. François, est-ce que tu peux me confirmer que c'est en plein écran chez toi?
Pour l'instant, c'est noir, mais ouais. Ah. Yes, that's okay. Yes, this is the full screen.
Toujours?
This is
okay.
Perfect.
Okay, thank you. Thank you for everybody to being here. I think we can first present ourselves with Vincent. So I am Matthieu Lain. I started spectroscopy approximately 1.5 years ago during the star party organized by Sheliak at the OHP. Perhaps I meet some of you during these events. I teach software design at university in French, but I have to precise, I am not an expert, a Python expert. And I think I have to apologize for my English. It is probably not clearly, but I try to speak clearly, and I have to apologize for my accent too, I think. So that's all for me. I give the mic to Vincent.
Yep, thank you. Hello, everyone. My name is Vincent Lecocq. I'm a researcher in the field of material design and material chemistry. And while I do some astronomy since I was a child, and spectroscopy for I think 4 or 5 years. And while I started to learn Python language which is the only a computer language I know. I think I started to learn maybe 2 years ago, and so I naturally melt astronomy and the Python language. And yes, we will show you some fun examples in a few minutes. So thank you for being here.
Okay, thank you, Vincent. So this is the first workshop on Python, and the purpose of all these workshops we choose here is to browse different uses related to the domain, so astronomy and spectroscopy here, and how to start with Python. It is a real challenge because I think we have all different skills in programming in Python, and we think first we can perhaps make a pool for what skills of everybody and adapt our tools here. So I will share you a link in the chat. Okay, so I share you a link, and I will share you the window. Here, if you want to you can also scan with the QR code or go on this link with your browser or with your smartphone to a quick pool about your skills in Python. I'll just wait. Everybody is coming, and I will activate it. So I will share again the link.
Yes, and the link is in the chat. You can copy and paste it in the chat.
So I activated it. Okay, so the question is about Python and your skills. Are you beginner in programming? Are you beginner in Python but not programming? Do you use Python a bit, or perhaps you're an expert of Python and you know it's easy peasy? So during this pool, I have also to apologize, I think, because I apologize for the Python experts, because we have to make shortness about programming here. We don't go in detail of software design. And I have to apologize to the beginners in programming, because we will pass quickly on some basis we need to sims for learn programming. But we can quickly see here you are there is a lot of you have a very good skills in programming or in Python, so we will try to adapt our talk for good listening for everybody. I wait a bit for everybody. I will take a screenshot after this presentation about this pool, and I will put it in the presentation. Presentation will be shared after the talk. Okay. Okay, I let the pool open. You can continue to vote if you want, and I will switch to the presentation. So thank you for everybody, to everybody. I switch. Okay, move again. We have the same tendency last week. Okay, I switch to the PowerPoint. Okay. Okay. I think that you see my screen. Perhaps it loads. So we will talk today about Python, and during these 3 workshops, And for first, today, we will talk about module in astronomy and spectroscopy. We try to organize these 3 workshops in progression, but the progression is not...
Matthieu, for the moment, I cannot see your screen. I have a black screen.
Okay, it's load, perhaps.
Maybe. So I see that you have switched to the sharing, but
yes.
On my side, I have a black screen.
Okay. I think it's the same for everybody. I restart the sharing.
Okay.
I think. Okay. Okay. Up. Okay. Okay. I activate it. Is it okay?
I tell you. No, for the moment, I don't see anything. Well, I see you, but that's it. Oh, are you still here? So
maybe we lose Matthieu.
Yes, it looks like we lost Matthieu. So Vincent, I can hear you. So it means the communication issue is not on my side. And well, I can see all of you. Sorry for this connection issue. For sure, Matthieu will reconnect in a few seconds. I hope so. Of course, this is a wonderful tool when it works. And maybe there is somebody who can sing something, or I'm not able to do it.
Francois, did you watch the Mars landing yesterday?
Yes, this is a good thing. yes, we have seen the Perseverance.
That was exciting.
Yeah. It's just wonderful. It's just wonderful.
Sorry for that. I think
yes, Matthieu is back. Matthieu is back.
Network breakdown.
Yeah.
Okay. Thank you. I try to share again.
Let's try again. Yeah.
I will.
It's just to put some pressure on.
Yes. I see.
So.
Yeah.
Okay.
Okay, so we can see your screen.
Okay.
Thank you. Wonderful.
Thank you, network. Okay, so we can go. So for these 3 workshops, we create a progression, but the progression is not linear. And we will talk about Python in 3 ways. First, we will see today Python for astronomy and spectroscopy. How can we use Python in this domain, and without installation and without go in detail in programming, just how can we do with Python. For the second workshop, we will see how to start with Python and what environments on our machines for play with Pythons. And in the third workshop, we will see testimonials and example with good programmers. We will present to us some works, some example. I don't say more. I keep the surprise. I think it will be a great workshop too. So as we see during the pool, we haven't not all the same skill in programming and IT. So we try to make indicators on each workshop for not the programming complexity, but how is it difficult when we start in Python for this workshop? And we have tried to precise it more in each workshop. So today we will we have take an example with first an introduction, context, tools, and software design reminders. And after we have again not linear progression in complexity. First, we will see consolidation of Gaia data. We will take a large example, large data, and we will zoom it by selecting and displaying an object, and display its characteristic, try to display and manipulating a spectrum, or our personal spectrum. And for the last, we will try to compare it with amateur and professional catalogs. But as we said just before, it is difficult to take for everybody the middle language for everybody, and we try to put indicators on some block, and everybody could take only the block interesting and play with it at the end, because all the code will be available at the end of this workshop. So let's go and try to play with Python and have fun. So first we will make a quick introduction on context at what is Python for the next. So Python, the Python language was born in 1989 during Christmas by Guido van Rossum. He started a personal project because
we still see your initial. Yes, okay. So now we have
okay.
the new slide.
I think for us, my network is not
maybe it's quite slow. Yeah,
in a good way
okay.
today.
But now we have history and philosophy.
Okay, that's good. And so the first the born of Python was in 1989, and Guido van Rossum, who created the language, searched a hobby during his Christmas holidays because his company was closed, and he created a new interpreters of script for easy to understand, easy to play with it. And so he decided to create this Python, and he called it Python because he's a fan of Monty Python. And the principle of Python is the beauty of the code, you know, like reliability, simplicity, fluidity, and really you want to something easy to read and to understand without complicated design or without complicated architecture. So we call it Pythonic code. It is a high-level code, so close to natural language, and it is an interpreted code language. Sorry, each line is interpreted and executed. And it is based on indentation. We will see a bit later, but we don't use a lot of programming structure today. We will just play with module for astronomy and spectroscopy. So we have as you should see a version and the date. We have some version on 0.5 to 1 to 3.8, and now 3.9, and there is a real shift between 2.7 and the 3 version. There was a real cleaning in the language, and there is no backwards compatibility between the version 3 and version 2. And the end of maintenance of version 2.7 was in 2020. There is another important information about Python here for us. It is dynamic typing. The dynamic typing is you know, we can consider the duck typing principle. It is, if it works like a duck, swims like a duck, and gossip like a duck, then it is considered it's a duck. We can traduce it by if you put an integer in a variable, so your variable is an integer. It is a bit complex about class, about methods, function, etc. But it is the principle, the global principle. So be sure no duck have been hurted during the slide preparation here. So Python, why it is so famous? Because there is some reasons. First, it is easy to use, versatile, and so it is easily assimilated by novice developers. There is a lot of libraries and modules for playing with Python. It is an open source language, and it is used by all and for all. There is a very large community, and probably if you have a problem on Python, you have just to make a Google search and you probably found the solutions. It is used by a lot of companies. I only mention here the big company because it gives ways for Python, like Spotify, Google, the NASA, Netflix, Disney for their animation, etc. And it is used for desktop application, web scripting, a lot of things. And the language have been powered here recently by data science and AI, because there is a lot of module, a lot of library, for scientific calculation and modeling, and scientific use a lot Python in some way. I put at the right of the slide ranking, two ranking, one of the IEEE spectrum. It is an English magazine by the Engineer Institute in Electricity and Electronic, I think, who make a ranking by a mix, social network, exchange, code productions, works offer, and it mix all of this measure and give us a ranking. We can see in 2020, Python was in first position. And we can see also there is one thing is not a very good point for Python. It is on mobile development, mobile software design. But there is something who will change probably in the future. Another ranking is Tube or Chobi, I don't know, who make a ranking with a mix about a lot of search engine and the request on this search engine, and give us a ranking. What is important here to see is only that Python is very used now and is on the podium. Okay, so let's try to play now with Python, and you have already Python installed on your machines. If you have Linux or macOS or Unix, you have already Python. I think it's a good thing to install the last version. And if you have Windows, you have to go to python.org and download the client package, the installer package, and install it. After the installation is done, you can open the command invite on Windows, or the term, the prompt on Unix, and just type $Python, and you have the interpreters open. So here we can type code, anything you want here, and here I type 2 + 5, I type enter, and 7 is the output. I can store value in variable. I can use function. So we have a real interpreter in Python. But we can have something greater, like IPython, and when you install Python, you have the PyPy, the package deposit, and we have an installer pipe with Python. When you can type pipe, install IPython, and you have a new interpreters, more interactive and with more function, like access to heads and docs with the question mark. We have self-completion, syntax highlighting, access case in, out, magic case, we will see later, and integration in most of editors. So what about editors? We have some kind of editors. We have Spider. It is like a MATLAB or RStudio-like. It is very interesting editors. I think we will see more in detail, like during the second workshop. You have a Visual Code Studio, you have PyCharm, and you have a Jupyter Notebook. We will see a detail after. It is not exclusive usage for these editors. For example, I use Spider for scientific scripting, for scientific test. I use Visual Code Studio only for scripting, quick scripting. I use PyCharm when I code a strong software with a big software design architecture, and I use the Jupyter Notebook when I want to share with somebody code with text. And today we will use kind of Jupyter Notebook. We will use Colab. Colab is a notebook online in the cloud. It is a Google tools, and it is so accessible with a Google account within the limit of 2 notebooks. 2 hours execution maximum when your browser is open, auto off after 90 minutes without execution. It is online execution in the cloud, as I said, ready to use, and you can download the notebook at the end for sharing or running on your personal computer. And it is free, and it's no cost, and it's a good point for us. And you can also have a better performance if you want to parallelize calc, or if you want to make AI, for example, you can activate the GPU or tensor processor unit if you want. The power is shared between a lot of collab, but it is an interesting thing because you don't have to create a big computer with a big graphic card. You can use here for free. So we will have cells, at the left, where we can type code and execute it. We have an interpreter in the Colab. We can move cells up and then downside. We can type text, and here you can see our running instance for our interpreters. A quick tour of programming about Python. Here, a variable allocation. We can put those 5 in the variable A. I take the references of A in B, and I print B. And we can see here 5. And if I make a new allocation of data in B, I print B, you have 2 after. You can make a multiple allocation, A, B, C, D, and the data. And we have, as we said before, with the generic typing, we have several data type, and we can put data inside, and the variable will take the data type of our data. So here I put 1 in A, 3.14 in B. Voiture, sorry, here the code is in French, but the code is the same, but sorry. I print A, and you have a type function like type A, and we can watch, you see the class is integer. So the type of the variable is integer, here float, and here a string. We have some methods or function on our variable like length, and here we have 7 characters. Sure. We have another data type like list. List for put data in and manipulate it, make table, for example. You can create it with hook, like this, and put every types of data you want in. It's very flexible and very useful. We will use it today. You have some methods or function you can apply on it, like that append for add data, that index for get the index of the value. We have also some dictionaries who works with storage of K values. You can see here the K1 and the value chain, the K2 and the value core, the K3, etc., etc. And you can access to the value with myDict and the K in the hook. It is a good type for us also. We will manipulated often, I think today also. And it is a good type for iteration, for example. Here is how we write comments. Comments line and document and source code comments documentation, and we have immutable tuples. It is a short object with a indexed order. It is immutable, so its shape is not modifiable. We can't modify its shape, but it is interesting because it takes less memory than list and dictionary. So we can use for the output of function, for example. And what is important for us today, it is module or library. We can import some library like NumPy or Matplotlib. Just by import NumPy as MP, I give it an alias. And you can create an array. It is a new data type. ND array is like you can create matrix. It is multi-dimensional table here, but you can only put inside one data type. If you put integer, it is integer. If you put float, it is float, etc. And we have a lot of method here, also already preview already exist in the module, and it is a very performant module. And module are often associated with other modules. Here we can work with Matplotlib and NumPy for make a graph. You know, you have NP is in NumPy, and we try to construct a vector here. And with Matplotlib as PLT, we can plot the value and show the graph. So we will use these two modules today, and it is some good modules. We have constructed this workshop only by using two ways on this module. You have at the right the PyPy deposit, where you can find, if you make a search about Matplotlib, you can see Matplotlib, the last version, and you can see pipe install Matplotlib, how to install on your computer or in the Colab. And you have a quick description and links. And the other website interesting for us is the official documentation, where we found some example for try Matplotlib and create script. So we have used these two ways for take information and try to play with Python. So that's all. We can just play now with Python, and I will switch to the Colab to introduce the code. So I stop sharing my screen, and I sharing my screen again. Okay.
That's okay. We can see it.
Good. Thank you, François. Okay. So we are here our workshop, our collab for this workshop, sorry. And we can see here the running instance. So Google give me 12 gigabyte for memory and 100 gigabyte for storage. I think it will be enough. And we have some cell here for where we can write text. You know, if I double click on, I have text, and I can write it. And after I have cell with Python code, and I can execute, I can run it. So we have the traditional hello world for code, Python code here. And we found the magic, so-called magic commands within in the IPython interpreters. And we will use it later. Okay. Thank you. And for example, %ls, we can watch what the files in the directory. And it is also possible, if you want, after to take this notebook and you want to access to your files, you can activate the Google Drive folder for you and access to your file. It will open a new browser, a new window, and it gives you a key, and only your file will be accessible. We can install module. For install module, it is pipe. We have seen this before, and you have just to put exclamation point and run it, and it will install the module in your collab. So we have some module here for this workshop: Panda for data manipulation, AstroQuery for consultation of astrocatalogs, Matplotlib for graphic visualizations, APLPy for visualization and astronomical graphical data. We have here bug dependencies about spectrals only on collabs. I think their version are not. There is a shift between the her version and the spectrals versions, and you have just to pipe install JSON schema and restart the notebook after the import, and it runs. So I install spectrals, IPy Aladdin, and IPy MPL, and we can now play with Python. So I give the mic to Vincent again.
Yeah. Thank you, Matthieu. So I will share my screen. So can you see the
yes,
the
that's okay. We
yes,
can
it's
see
okay?
the Gaia notebook. Yeah.
Yes.
Okay, thank you. Yeah, so now that that we have installed these modules, we're going to play with it, and I'm going to show you an example which I have taken it in a publication of the ESO Gaia team. So you will retrieve the link here in the notebook. And we're going to see in this example how we can make some queries in professional database, in the Gaia database, for example, and also in Simbad. And from these queries, how we can plot, how we can make some nice plot in order to at the end we just want to make the HR diagram, Hertzsprung-Russell diagram of an open cluster. So we're going to play with that. So well, okay, we call here the different modules that we will use just hereafter in the code, and then we'll have to make the query in the Gaia database. So the queries are based on another language, which is SQL language for a structured query language, I think. It's quite different of the Python language. So, well, the first thing for me, the first thing I've done is to see to look at the Gaia team example of SQL language, and here in this link you will find a lot of different queries depending of what you want to query. If you want to query stars of globular clusters, or if you want to query R Lyrae, for example. You will find many examples, and here I've just taken one of them and just make a very small adaptation. So the SQL query looks like that. It's a kind of it's a text variable, and we just put in the query what we want to retrieve in the Gaia database. So we want to retrieve the source ID of the different stars, their right ascension, their declination, their parallax, their proper motion in right ascension, the proper motion in declination, and also different magnitudes, so that we will be able to plot the HR diagram. And also, of course, the color index, which is the difference between blue and red magnitude. Okay, so we want to retrieve all that from the new Gaia EDR3 source. And well, it's a kind of virtual telescope, you see. We are going to point it to an open cluster which is the Pleiad, so M Messier 45. And this is the coordinates of this open cluster. So we're going to point our virtual telescope to these coordinates. We have a field of view of 1 degree of radius. And yes, and here we have some lines for just to make just to retrieve some only the good quality data. So this is just these lines are just to filter the good quality data. You will find this filter. I've not invented anything. You will find this filter in the link here. It's exactly the same thing. Okay, so then that we have written our query, we launch the search. I didn't do it here because it's a little bit long. Here, I think we will retrieve 10,000 stars, and the query just take maybe 1 minute, so it's okay. But if you make a query of 2 million stars, for example, that can take several tens of minutes. So it can be a little bit long, depending on what you are or what is your request. Okay, and now I have my result, and my result is here stored in a table object, which present like this. Well, it's not very nice, but we have all we want. The source ID, so the Gaia identifier of the stars, and the right ascension, the right ascension error, declination, parallax, and so on. Okay, but from my point of view, I don't like that kind of table, and I'm more used to work with another modules in Python, which is called Panda. And the object of pandas are called data frame, which has kind of tables, which are very convenient to play with pandas data frame. It's very easy to manipulate several thousand or millions of rows and to make an operation on it. So I will, in the next line, I will convert this astro table to a pandas data frame, and that's just that I'm doing here. And I just recover the data I need, which are the source ID, the right ascension, the declination, the green mean magnitude, and the proper motion, parallax, and the color index. And then I built, from that, I built my my pandas data frame. And here it is. So this is the pandas data frame. So and we will with that data frame, we now we are able to make very simple plots, and in a very simple manner. I mean. So in this data frame, I've got still have the ID of the stars, right ascension, declination, and all I need. Okay. So now I want to have some visualization on my virtual telescope, and here it is. I plot all the stars that are here in a diagram of right ascension and declination, and here it is. So this is, of course, M45 open cluster, as you can recognize it, I think. No, there are several thousand of stars in it. And of course, M45 is in the eyepiece here somewhere. I don't know where exactly, but yes, for sure it's here. But also, if I want to build the HR diagram of this open cluster, I have to take into account only the stars which behave to the cluster, and many of them here are not part of course, of M45. So I will have to select to find a way to select my open cluster in all that stars. Okay, so how we are going to do that? In fact, a good point for an open cluster or for a globular cluster, for example, is that all the stars in that cluster have the same displacement in the sky. They have the same proper motion. So maybe if I make a plot different of right ascension and declination, but if I make a plot with the proper motion of all my stars in right ascension and the proper motion in declination, maybe I could find my open cluster. So here is that plot. We see 10,000 stars here, represented here, with very large values of proper motion in declination and right ascension. But the advantage of a Plotly module is that it's quite interactive, and I can zoom. I will zoom in all that stars. Okay. Okay, so here we are. This is all the stars of my Gaia request. You can see a very large, how to say that, very large amount of stars here with a very large value of proper motion. And here is something which is quite interesting. On very small value of proper motion in declination and right ascension, I've got a spot here, which is quite interesting. I will continue to zoom on it. All right. I think maybe it's our open cluster because we have very tight values of proper motion. All the stars here have a very near value of proper motion. So maybe it's my open cluster. So okay, I will take all that stars, and I will plot the HR diagram of all that stars. So I will make a selection of that stars. So I have some lines here to filter my pandas data frame, and just in order to recover just that stars here. Okay. And well, I have now a new table which contains now 400 of stars, and mainly most of them have quite values of proper motion and proper motion in right ascension and declination, which are very identical. So I think here that I have 400 stars of my of the open cluster, and from that now I can plot very easily the HR diagram, which is here. So this is the M45 open cluster HR diagram, representing here the absolute magnitude. I don't show it, but we have made the calculation from the Gaia's magnitude. Where is it? Yes, here. In that line, we've made a small calculation in order to retrieve the absolute magnitude from photometric magnitude here and the parallax. Okay, so that gives us absolute magnitude here in ordinate, and here on that axis, the color index. So here is the HR diagram of the Pleiad cluster. We can see that there is no red giants, no red hypergiants here, no old stars here. This is a typical HR diagram of young stars, and young cluster. Here on that plot, on that image, I superpose this HR diagram of M45 open cluster to a 2 million HR diagram also requested on the Gaia. And we can see here in blue, of course, the main sequence, and the M45 stars are mainly all on the main sequence. And here you can see all the stars and the red giants which are here, and maybe here, but it's very sharp. We can see here the white dwarfs also. Some of them lies here. Okay, so M45 HR diagram cluster, very young cluster. But this cluster also contains some quite interesting stars, which are B stars. I mean, this is stars which have some emission lines in their spectra. Spectral type B spectral type, and with some emission lines, and there are some B stars in the Pleiad cluster. So we are going, yes, to find them and to represent them, and it's a kind of another way to be sure that in all our Gaia query of 10,000 stars, it's a kind of way to locate the open cluster. You will see. Okay, so here we make a Simbad query object. So a query in the Simbad database. Very easy. We just try to find a Pleion in all our initial database. So we made a Simbad query object on Pleion, and this return here I return the result in a pandas data frame, which looks like that. Here is another name of Pleion, 28 tau. Its position in right ascension, declination. And something which I'm interested here is the Gaia ID, which is here. So I'll take this Gaia ID here, and I will search for that ID in my first table. Okay, where I had, if you remember, I had 10,000 stars. I will search for Pleion in that table. So it's lines which are written here. I try to locate this ID, this Gaia ID identifier in my table, and it has been found here. And this is the good, you can check, this is a good right ascension and declination for Pleion. Okay, so now I return to my virtual eyepiece, and we'll try to locate Pleion in that eyepiece. So I plot here another plotly scatter plot. Sorry, and I just add to the previous plot. I just had the position of Pleion that I retrieve here. Okay, so yes, Pleion is here. That's nice. Okay, I can zoom it. This is an interactive plot. Okay, and if you want, just after this talk, you will have the possibility to play with this notebook. And another funny thing is to retrieve all the 7 sisters of the Pleiad and to plot here and to plot them. It's so that you will be able to see all the cluster that we have to what we are used to see and to see in the sky. But here I represent only Pleion. Okay, so if I go to the other plot of the proper motion plot, you see that previously I just zoom on that part, and then zoom on that part, and I said, okay, M45 is here, but maybe I was not really sure. But now that I know where Pleione is, I know that Pleione is in that spot of stars. So well, okay, I'm sure that that spot of stars is the open cluster I want to look at. Okay, I reset the axis. And then I still can plot my HR diagram and then locate Pleione on that diagram. Okay, so Pleione is here in the upper part of the diagram, at the left of the diagram, which means that Pleione is okay, it's a young star, and it's a very, very hot star, because I don't know if you are used to HR diagram, but here in axis, it's an axis which represents the temperature. Here are cold stars, and on the left, hotter stars. Okay, so and you can play with that. After that, you can represent all the most all the seven sisters of the open cluster, and you will see that they are all very hot stars. They lie all around the Pleione. Okay, so that was some funny example of query of the Simbad database and the Gaia database. Maybe another example. Yes, with Simbad you can also you can make a query on a particular object, on a star, for example, or a cluster, for example, or many things. And you can also make a query on a particular region of a sky. So that I made here, and I enter the coordinates of the M45 open cluster, and I make a query around this region, and okay, Simbad found Melod 22, which is the other name of M45. Okay, so well, just to know that while you can perform some queries around the region. Sometimes it's useful. And also you can say to Simbad that you want to retrieve not only the right ascension and declination or the name of the objects, but also their spectral types. For example, if they are present in Simbad, of course. And okay, so I make the same query in a region of the Pleiade open cluster with a radius of 2 degrees, and I put the result in a pandas data frame, and so it returns me some I don't know 4,000 rows, so 4,000 objects, and in these objects sometimes there is spectral types, not always, but sometimes we find them, so some stars. So I'll make some filters on this pandas data frame, filters about the spectral types, and I will just look for the B spectral type stars. Okay, or I will also have a look to the stars that have some emission lines in their spectrum, and I apply this filter, and I recover a new data frame, which are all the stars that have some emission lines in the spectrum, whatever the spectral types here, M, B, K, whatsoever. But okay, so I have in the region I made the request, the query. I have I don't know how many. okay, I have 54 stars in that region around the Pleiades, which have some emission lines in their spectrum. Okay, so that's another example of things that you can query in the SIMBAD database. Of course, you can also have some visual display with Alada. So I make the same kind of search. I put here the coordinates of of the open cluster of Melod 22, or I could have put M45 Pleiad. I think it can also work. And then I ask, in fact, I ask this code to find a picture, and in the DSS catalog to find a picture of this region. Okay. And then with Apple Pie, I can we can print the picture of the M45 open cluster, which is here with the coordinates in right ascension and declination. So there are many things, many ways to print pictures with Python. You can also there is also a module in order to call the Aladdin light in a cell, and you can play with Aladdin light if you were in the Aladdin light site. It's the same thing. Okay. So well, that's with this small example. We just wanted to show you some of the possibilities of the queries you can perform. The queries you can perform in the professional database of Gaia, for example. There are many funny things you can perform. HR diagram. You can locate some stars in the Milky Way, for example, with galactic coordinates. Well, you can make many things about with this database and with SIMBAD also. So that's all for me. Now I will let Matthieu continue. Thank you.
Okay, thank you, Vincent. I will share my screen too. Okay, I hope my network will be okay. Okay, you will see my screen. Yeah. Great, thank you. Try to perhaps in full screen. Okay. Okay. So we have we have seen the visual display of Aladdin, and we have zoom in the M45 and select Pleian. We can now try to watch our spectrum of Pleian, perhaps, or take spectrum from base, for example. Try to do it. There is a two different solution for us is for making this. I start with the second, sorry, with the B, and we can try to request to get spectrum from base database because it is a BE stars here, Pleian, and we can go to the web interface of base and make a query in the input field, search some spectrum and download spectrum. Or we can also take our spectrum after a spectral session with your scope, perhaps, and you have some fits to show for your spectrum. There is another way sometimes we need to get a lot of spectrums and pass and go from the web interface. Could be long if you want to download 30, 100, 200 spectrum for process, perhaps for time series, for example. You want to have another way to download it, and both have an interface, a protocol who can be queried. It is a simple spectral access protocol who gives very table format data type. I play with it for personal uses and try something. And I want to make a Python script for query and get this spectrum, but I found a problem for me because the VO table is in 1.0, and with Atropy, I couldn't access to this data and parse it, because with Astropy we have in 2 lines a module who can parse this format, this data type with VO table. It is not really a bug or a little mismatch, but this I couldn't do this. It doesn't work. So I doesn't want to download each spectrum or make a package, etc., etc. I just want to do in Python because I think it was fun. And on the publication on the base database, we can see how it works, and we can see you have the link with SSA, simple spectral access, and you pass you put some parameters like position, like the size around the position for search, the spectral band, the start here and the stop, a time period with start and stop, and it gives you an XML return, some return, and with all the spectrum and links to download it. To download them. So first we try to get the codes of Playon. We already done before, but for be sure I redo. So I have sky codes of about Playons, and if you take this this link, so you have a return of data from base. So the return is, if you line by line, it's not very readable. It's not a great representation. So I use preprint. Preprint is is like print, but with indentation, with a great representation. And I need the web request module called request for just make a query on a on a link. So I record the link here. It is this link with position of Playon, the size around the position, and the spectral band 4,000 and to 6,700, and a time period. Okay, so I can make the request, who take in parameters the link, the URL, and it gives me a response, a code status. If I print it, I have the 200 response from Apache server. 200, it is everything is okay. 404 page not found, etc. So here I can take this response and get the text on it, and I will have the response, the query, the response, the return of the query in XML. And you can see here there is a version 1.0, and Astropy work very great with 1.1, 1.2, 1.3, and here I don't found the solution at first, but someone from the first workshop in French gives the solution. Jean-Luc Martin have the solutions. There is a bug between float and integer here, so thanks to him he will optimize my code a lot. But for this workshop, I work, and for my process, I just try to play with it, and you can see so XML code with Immutable tag, resource tag, description. You have a lot of field, and we have another field. The first here after the table tag is it is the meta ref URL. So it is a dataset access URL, and it is a link to the feeds. So we can use it for download feeds after. You have the meme type of dataset, you have a dataset model, you have publisher, etc., etc. So there is a lot of fields, and if we go down, we will see, okay, we will see after all the field tag, we have a data tag, table data, and here the TR and TD. TD like a table. And we have first the link. The first link we've seen before. It is where we can download the feeds. We've seen the meme tip. Here it fits. We can see the publisher, etc., etc. We have a lot of information, and we have every spectrum we search by the query. So we can iterate on it. We can request and get all the data. And the Immutable module in AstroPy do it very quickly and very good, very well. So during the script construction, I didn't find the solution. So I decided after some times of search, I decided to create a parser for go quickly, and could manage and could manipulate this data more easily than take copy and paste, you know. So for doing this, I download a module. I try to use a module for parsing. There is a lot of parsing module in Python. I make a Google search and I take XML2DIC. It does a job. I install wget for download some files, etc. And let's go. I try to create a parser. So I import XML2DIC, I import Panda, and with XML2DIC, you can parse your XML, so r.text. And I put the object in a global dict, in a dictionary. And after that, I can move in the object and go to the tag I want to get data. So global dict, you know, here, view table, resource, table data tr, and now I have access to the data and TD, and so the spectrum. So I decided to create a data frame like a table in Panda, and I iterate on each item in my entries list, so in the data. And for each item, I create a new dictionary, and you know, you have the K here and the data, and I take the item 0, 45, 46, etc., who corresponds to here. 0 is the fits URL, the fits link for download it. And when I create my dictionary, I append it to my data frame. And so here I'm in the iteration, and after that I show the data frame. So I have the link, I have the target class, a star, I have the target name player, and the meme type, the format of the file. So that's a good point for us. And now we have the link for the feeds, so we can download it and keep and get more information perhaps. So I take the same code and I open the feeds to get the header information. So in the same way, I create a data frame, I iterate on, I just run perhaps. I iterate on each item, and I try to download the link, the feeds, and I open the feeds with feeds AstroPy that open, and I get the header. I create, I make this this code, this process in a try except, because it is a input output a process, and we encapsulate it with a try catch or try except. You know, if there is an error, it goes to the top of the backstack, the software backstack. So we catch it for print just an error, error downloading fields file, but not crash crash more. After that, I create again a data frame, and now I put it inside the header fields resolution and the date. You know, you have access to the header, so you can put in your data frame, and I add this dictionary, this row, to my data frame, and I can show it again. There is ascending order. So I have the creation date from the header, the fields URL, resolution, target class, and the target name. So we can play a lot with it. For sure, we can. I can use the first table for doing this, but like Vincent said before, data frame from Panda is a very good object to manipulate and watch data and watch a big data. I just write here if you want to use perhaps after. The list of items I found interesting for me. I not put here all of the items, but you can find some of them. Don't execute because it's just for notes. Okay. So we can now, with our data frame, our table, we can get the fits again. So I make fits open wget that dot load, and the first line, because our table begin at 0, and the first column to get the fits. And after that, I watch the table, and we have the wave of the spectrum and the flux. I don't plot it now because we will see the other way to get spectrum, but we can now plot spectrum with this data from the base database in Python. So the second solution is to retrieve personal data, to use personal data for make a plot spectrum. I use here a little tool from Google Colab, where you can select files from your folder. If you use Google Drive, you can use this. I put it after, so you can just put the paste, to your file, and it will be okay. So here it load the file, and I can access it and watch the information here. So float 32, sorry, and we can get information about it, the header and the data. So I print the header here. We get all the information. It is a spectrum from the base database made from Christian Buell about Lain, and we can try to prepare and display it. I use Spectral library, a Spectral module, who was born 4 years ago. It is a library dedicated to spectroscopy in astronomy. And you can load, manipulate, analyze spectroscopic data. It's a very interesting library, I found. And we need two other data type or usage function for making our spectrum. The WCS, the World Coordinate System in AstroPy, who will get the keywords in our header to make the step of the wavelength, and we use units to specify the units of our data, because our data in spectrum are floats, and with unit from AstroPy, it is a data type where you can give quantity to our data, and when you multiply your values with the quantity, you have a dimension quantity. So we will use it. And here is the example. Just want to record. I import so astropy.wcs. I import units, and I import spectrals. Here I only need spectrum 1D, and we will see later spectral region. So here I set units to my flux, so data multiplied by units that Jansky, and with the CS object fits WCS, we can apply the WCS methods and give a parameter header, some case C delta 1, and you put the header C delta 1. So it needs all this information from your header, and after that you can create your spectrum. It is a spectrum 1D object who give two parameters, who took two parameters, the flux, and here's the WCS data. It is your wavelength, the spectral data. And I can display this object, and here we have a spectrum 1D, we have the flux quantity, the values, and the spectral axis. There is another way to make it without the WCS object here. You can just create your user preparation about spectral data with this the header and calc the step for the max, the ref pixels, etc. It is a code, a short code from Jacques Michelet, who share it approximately 1 year now, and it works very good. It works well, so you can use this too if you want. Now we have our object, we can plot it. So we just have to use matplotlib. I make a plot, a figure here with subplot, a size, and to my axis, to the plot, it took two parameters here, the spectral axis, so my spectral axis. I give it some units, so units that angstroms, and the second parameters here is spec.flux. So I set axis x-axis title. I set here axis title. Also a grid, I set the grid with color, etc. The legend value. I said here you can put the legend in the best location you found, and I create also a spectrum title with the header information I get before, the object name, the date, the date observation, etc. And after that, we can show the plot, and it seems good. We have the spectrum here. With matplotlib. You can also save your figure to PNG before. I think it is important to make it to do it before the PLT show, because when you done the PLT show, the figure is not keep in memory, so probably your PNG will be blank. But you can record the figure references in a variable. To keep it, you can show, and after you can save the PNG whenever you want. Okay, you are just to save the reference for use it. So okay, we can also make more manipulation perhaps with this library. Because Spectral provides some useful feature like continuum fitting, line finding, modal line fitting, etc., etc. I put the links for more information and in the source at the end. So okay, how does it work? We have to import astropy modeling, fitting, and speculative fitting. Sorry. First, I keep the previous spectrum values in some variable for showing the two spectrum, the spectrum and the continuum, you know. And I use the method fits generic continuum, who took two parameters, the spectrum for the continuum, and exclude regions. You know, if you want to exclude Balmer's lines, here I exclude a portion like 3600 to 4000 for the function. Don't take it for the continuum. And I use the function GLFit. We take the X spectrum initial data, okay, and after that I create the plot. So here, create graphic creation, the figure, the plot, the two plots, and I show it. And we have our continuum here. It seems to be good. Okay, now perhaps we can go again forward and try to divide the spectrum for normalization of our spectrum. And I make the same work, but after that I divide it. So it is the same code here, you know, and I divide it for my spec normalization, and I plot it, and here it is. So that's good. We can go again. Perhaps with this spectrum normalized, we can find a line with the function of spectrals. So we import find line derivative and find fit lines. Sorry. And this function which finds lines by calculating the derivative, then setting a threshold based on it. You fix the threshold here, and you give it the spec normalized on the function find line derivative, and I print so the variable here. I print some lines who was tagged with emission value, and he found a line is here 6. So the H alpha line we have an emission. It's true. And if you set the threshold more precisely, you can detect a little or a big line if you want. So it's good for us. And perhaps we can now, we have the value of the alpha line. It detects an emission line, and perhaps we can play with it. So I have the value. I can perhaps try to cut a part of the spectrum to make a zoom, and perhaps I can try to get some analysis value with spectral just for try and play with the library. So I import spectral manipulation, extract region, I import spectral fitting, estimate line, and centroid and equivalent width. First, I will create a spectral region. It took a start and a stop region. So here I have the value of the H alpha line. So I take the value and create a region around in angstrom, in units angstrom in AstroPy. So I have my object spectral region, and I can use extract region for extract the part of the spectrum. So it took a spec normalized, 2 parameters, spec normalized, and the spectral regions. Okay, so now I have a subspectrum with the extract region, and I can create a spectrum 1D like before. Okay, and I will be able to plot it, and I try to use also equivalent width, which took also 2 parameters, a spec normalized and a regions, and also centroid with the same parameters. I plot it, and I have the values, the zoom on the H alpha line. Sorry. So it is a good way. It is a good point for us. So we can try to make analyze and give some values. There is other library to make some plots, to make some graphic outputs, like Plotly. It is something. It is like Matplotlib, but with dynamicity more advanced. We can just create. So I import Plotly. Create a figure, go that figure. I add a trace scatter with X and Y axis, the mode, the name, and layered configuration, a title, X-axis, a title, etc. And I show it, and we have a plot with more dynamic. We can zoom again in the way. We can take a picture. We can go home. We can no, sorry, move in the spectrum. It is very interesting. An interesting module, very interesting library to manipulate and play with our spectrum and give some value on the line. Okay, so now we have our spectrum. We can get some spectrum from base, a lot of spectrum. Perhaps we can try to compare it with some professional catalogs and try to do it with Python. There is another module like Pivot who can we can use for perform queries on virtual observatory virtual observatory protocol and consult and get information from professional catalogs. So I install it, pip install Pivot. I get the player coordinates again to be sure. Okay, and now I active the IPython here notebook for show all of the output of the cells, because when you have a lot of traces, the output will show you the start and the stop, but hide the middle. And here I want to show all of the catalogs, and I want to select it. So I ask him to show everything, and we can consult the register. And when we have selected a register, we can ask him, make a queries on it with the SSL protocol, simple spectral access like before, and perhaps search a spectrum. So here I use Pivot for console registry, and I give it a keywords with so registry research, and I use research with parameters keywords, and I ask him the keywords LOD for the spectrograph and the OHP. And I iterate on each on the result. It is the same process, or we do here the same thing like in Topcat. You know, when you search something, you have the catalog result. It is the same way here. And we have all the catalogs. I iterate on it. We have all the catalog with the link. And at the end, at the second to last result, we have, okay, the OHP with LOD, and we found it the SSA protocol. So I can use it. We can use it. I take the link, and now I will use the SSA service. So VO dal service, and we take the parameter in parameter the link I take before. Sorry. And I make a SSL search. Sorry. Okay, I think we can go. Oh, just watch. Okay, it is an emotion. So we can use SSL service that search, who took 2 parameters, the position and assigns around the positions. When we have the result, the SSL result, okay, with the SSL result, we can iterate on it again and watch the output in the cell. So we have here all the spectrum from LOD, from the catalog of LOD about play on, because we give it the position. We can also make it with base, because in the registry before we found if you put the keywords base, you will find the same links. Here I make the request on it. So here I have all the result the request with some of spectrum, and I can take one of the spectrum and download it for show. So I take again wget and astropy.io and I create a wget download on the link. So I take this spectrum 21 and I open it with fits AstroPy, and I show the header. And I print the value, and here we have the flux and the spectral data. So, okay, let's go, we can display it. We can display it, and here we have, we can make the same code like before with Matplotlib and Spectral. So I run it, we have the Spectral here, the spectrum 1D, but here we don't work with with the WCS. We use only data, and we have the K-word wave and the K-word flux. So I have just to create a figure and plot it. And okay, we have the spectrum with a big emission on 2 lines. It is not the same date in comparison of the Christian Briel spectrum. It is before in 2013, I think. So perhaps we can compare it. So I create 2 plots, 2 subplots here, and I pass the 7 and 8, so the Christian Briel spectrum and the Elodie spectrum, and I plot it and I show it. So we have the 2 spectrum. It's a good point for us, and perhaps it is important to compare what is comparable. So I will take a spectral region of the spectrum for compare it with the second. So I reuse spectrals. I create a spectral regions. Okay, I apply it on the Christian Briel spectrum with the extract region, and I create a new spectrum 1D, and I make the same thing on the Elodie spectrum. And I plot it, and we show we have the 2 plots, not the same resolution and not the same date, but we found the element at the same position, and we have 2 spectrum of Playan, one personal spectrum, and the other it is a professional spectrum. So it's interesting because with Python we can access a lot of data and play with it a lot. I think it's a bit fun. For finish about the code, I have to show you a last thing. I call it bonus, but I don't know if it is a bonus. Perhaps it's just a cool stuff. I suppose you plan to build a spectroheliograph in the year. I talk about the Christian Briel Solex project. Which is a very good project. I think very interesting here, and I think I will create also one Solex. I will try to make it one, and I ask myself. What about the sun and Python? I don't really manipulate a lot the sun. I took some picture, but I ask myself, okay, what about Sun and Python? And I found the SunPy library module library who can permit us to consult and visualize data of sun's observations from different instruments, including the SDO. Okay. So we try to use it for get sun image, and we will need some dependencies like SunPy, like AstroPy, like Matplotlib, etc. A raw project we will see later, and Pillow for watch an image. So okay, so with Pillow, I just get the image of Christian Briel who post on the forum Astrosoft. He post an image 29 November. I just take the link of the image and I show it with pill image. Okay, so image.open. I put it the request, so the link, and here is the image. Okay, so now let's try to play with SunPy. SunPy, I install it, okay. There we will need units of AstroPy, and sunpy.net, we have to import Fido. It is a downloader client, and ATTRS for use the request. After that, with Fido, we can make a search with the function. It took a time period, start and stop, an instrument, the AIA for atmospheric imaging assembly instrument, which can take picture of the solar atmosphere in 10 different wavelengths every 10 seconds, and a wavelength here who interesting us. And I print the results, so we can see here there is I hope it will work. Yes, we can see we have result. We have image at the date of 29 November. Okay, so we can download it. I download it, and we can plot it with Matplotlib. So it's very cool. We can get data. It is the same work when you go on the website and you make the search from the web interface, but here it is in Python, and we can retrieve the data and play with it. Cool. We can also make an overlay with two instruments. So image taken by IR and HMI, the helioseismic and magnetic imager, okay, who takes maps of the magnetic field and the speed of the sun's surface. And for overlay, to perform an overlay, we need to reproject the new reproject module. So I install it, I import it, and I set a figure I set the figure size better because it is a beautiful picture. And capture here is for hide the line of installation of download trace. You know, there is a lot of files, and it creates a lot of traces, not useful for us. So with capture, you can hide it. In the same way, I create a data period, time period here for start and stop, and instrument wavelength parameters for IR and HMI, and I create the search with the two instruments. I don't create or invent here anything. I just take here from the documentation of SunPy for play with it. Okay, and we have the files, Fido. We can fetch on it, and with this we can make a graph preparation. You know, so resample and create the map, and after that we can plot it with Matplotlib again. And we have here the HAEA sun and sun image, and the HMI magnetogram here. And we can see there is the shift or differences between the visualizations. So that's why we need reproject. The reproject module for this, and reproject will be we can permit us for take the WCS data and reproject the shape in the good way between the two images. Okay, so you can access, like we've seen before, with the double question mark the documentation. So if I run it, you have a pop-up at the down. We have the signature of the function with input data, output projection. Okay, so let's go. We can use it. Output footprint, and I use reproject. We take some parameters for the two image and the two image shape and the WCS to reproject the visualizations, and we can plot it again, and we have the good visualization here with the magnetogram and the IR visualization. That's a good point. Perhaps we can overlay the two graphs. So with Matplotlib, you just make a projection, and we have the two image with the AR and the HMI visualizations, and it is very interesting and beautiful picture I found. So here it is. We have done the job, and we can perhaps compare it with the initial image of Christian Buil, and we can see the solar activities here with a shift in the hour, I think, between the two images. I don't find the good error, but it's quite cool. Okay, that's all for me. I hope it was interesting and it will be useful for you. I just have two things to tell you for stops. I go to my PowerPoint. Okay. Click. Okay. Did you see it in full screen?
Yes. No, it's
okay.
It's full screen now. Yeah. Perfect.
Okay. Cool. Okay. So we have played a bit, and I just said some books. Most of my books are in French, but there is the Learning Scientific Programming with Python. I found it interesting because he talk about SciPy, NumPy, Introduction in Python, etc. I think it is a good books too. If you can find the translation of this book in French, I found it interesting. Precisely this for beginners, Python for data scientists, who the most of the book are about introduction about Python, and it is very precise and short. I think it was interesting. And this Python for the physics, for a physician, French physicians. He talks about geometrics with Python, geometrics optics with Python, and visualization data. So perhaps we can find the translation if they are translated. I put also some links for start with Python. For sure, you have the official documentations. The links, I put these links of the ARAS forum of Python on astronomy and spectroscopy in interesting links. A post I've done 1 or 2 months ago, and some links for Start Python and Play with Python if you want to go forward. And for finish, you will find the video, the presentation on the Sheliak YouTube channel and the source code Python on the GitLab. On my GitLab, you can go to folder workshop Sheliak/AN, and if you want to talk, share, need help or whatever, you can for sure contact us. It will be a pleasure. Thank you for listening. I hope it will be interesting for all of you. Okay, that's all for me. Thank you.
Mm-hmm. Thank you very much. Thank you very much, Matthieu. Thank you, Vincent. I think it was great. We have some good comments. We had a question earlier, but Vincent, you did answer. So are there any restriction on querying the databases like Gaia or Simbad, or can anyone ask for data? And you replied, Vincent, that there is no limitation. You even don't have to register. You can access all this data, which is really something wonderful. So you can make your own data and compare to all what the humanity has already done. Well, I don't know if you have questions, so it's time if you want to ask questions, don't hesitate to open your mic. Maybe I can just do a small comment because you talked about at the end, Matthieu, you talked about the Solex project.
Mm-hmm. Yes.
Maybe I'm not sure that a lot of you are aware of that. This project is managed by Christian Buil, and this is a small spectrum made based on the 3D printing parts, and this is something just amazing. And we have a subscription ongoing. But so far, Christian Buil he made a huge website about this project, but it is only in French so far. But I know that he plans to translate it in English and then to share that with all of you. But this is just a wonderful instrument, a small instrument that you can do in the do-it-yourself mode. And the idea is to have a spectroheliograph, so you can take some images of the sun. and like you showed, Matthieu. So again, if you are not familiar with this name, just to look at Solex on the AstroSurf forum, for instance, and you will find all the information. Okay. Any questions? So I see a lot of thank you, congratulations, and so on.
Thank you for your comments. Thank you.
And again, well, if there is no question, nobody wants to open the mic.
Douglas Ben has a question.
Yes, Douglas.
Could you please put up the URL that you showed at the end for your notebook? That's where we were looking all the information you've been programming, yes?
Yes.
Can you, yes, if you could please put that back up, thanks.
Yes. I try to share it.
Or even put the link in the chat, that would be good.
Is this?
For now,
I think it was gitlab.com, chronocastro,
yes.
Python.
I was a link to the notebook. Okay, sorry.
Yes.
Yes. I'll share the
PowerPoint
PowerPoint
that you were showing us.
Yes. I don't share the good things. Okay.
Anyway, so I remind you that Olivier is with us, even if he cannot speak. I guess it is very frustrating for him. But Olivier will put all the video and will send a mail with all the information where you can find the presentations and so on. But so this is the information.
That's it.
Okay.
Thank you. And this is where it says source code Python notebook workshop #1. That's what we've just been looking at. Is that correct?
Yes, absolutely.
Yes, thank you.
All the workshop will be all the workshop will be downloadable at this link, and I think perhaps at the end of the workshop, I think Olivier want to create a package also. Olivier and Francois want to put a package, but you can take the notebooks and the data to play with it at this address before the end of the workshop. Yes.
Thank you very much.
Okay. Any other question? Well, then I will stop recording. I will tell you, all of you, thank you for your attentions and attendance, and we will continue in the next workshop in a few weeks. Okay, thank you very much. Have a good day.
Thank you very much.
Have a good day.
Thank you.
Good night, and see you soon.
Night.
Thank you.
Bye-bye.
Bye.
Thank you.
Thank you.
Bye.
Thank you. Bye.